Today we are here with the module 2 of the chapter 2, that is magnetic effects of electric current. So let's begin this module. First of all, we have the force on a current carrying conductor. So what is this? Let's discuss. Watch here. We have a conductor which is connected to the external circuit with a cell and a key or a switch, and two poles of a magnet, two opposite poles of a magnet, north and south, are here. So the magnetic field is produced from north to south. This B represents the magnetic field. Okay, in this condition, this wire is here in the external magnetic field. Alright, now what happens when we turn this switch on? What happens? Watch here. When we turn this switch on, an electric current starts to flow in this circuit. Right? So we know that a current carrying conductor is associated with the magnetic field. Alright, this current carrying conductor will be associated with the magnetic field, but another or external magnetic field due to these poles is there. An external magnetic field is there due to these two poles. So the magnetic field associated with this current carrying conductor and this external magnetic field due to these poles, these two magnetic fields will clash each other and there will be a force on this conductor. Due to this clash, there will be a force on this conductor like this. Due to this current supply, it is associated with the magnetic field which clashes with the external magnetic field, and this current carrying conductor experiences a force F. Alright, so we can say that a current carrying conductor in the external magnetic field experiences a magnetic force. The magnetic force is given as this: F is equal to ILB sine theta. What are these symbols or representations? Let's discuss. Where I is electric current in the conductor, L is the length of the conductor, and B is the external magnetic field, while theta is the angle between L and B. So this is the way we have defined the force on a current carrying conductor. But watch here, we have represented this force downward. Why this force is downward? How can we define the direction of the force on a current carrying conductor? So we have a rule to define the direction of the force on a current carrying conductor, and that rule is here, which is called Fleming's left hand rule. What is Fleming's left hand rule? Let's discuss. Watch here. Here we have our left hand. This is the left hand. Okay, in which our thumb, index finger and middle finger are so adjusted that each two fingers have an angle 90 degree between them. Each two fingers have an angle 90 degree between them. So in this condition, if we represent the electric current with the middle finger, magnetic field with the index finger, then the force will be represented by the thumb. Alright, so what is Fleming's left hand rule? If we stretch the thumb, the index finger and the middle finger of our left hand such that they are mutually perpendicular means each two fingers are having the angle 90 degree between them, then the middle finger represents the direction of current flow, the index finger represents the direction of magnetic field, and the thumb represents the direction of force. Now let's start the electric motor. What is the definition of electric motor? We will see here. Watch here. Here is a table fan. This table fan is having an electric motor inside, due to which these blades are rotating. So what are we doing? We are giving this fan or the electric motor the electrical energy. We are providing it the electrical energy, and this fan or the electric motor is converting this electrical energy into the rotational or mechanical energy. So we can say that it is a device which converts the electrical energy into the mechanical energy. Now let's move to the principle on which the electric motor is based upon. What is this principle? So let's discuss. Watch here. Here you can see a rectangular coil is placed between two opposite poles of a magnet, and this rectangular coil is carrying a current I, which is supplied with the help of a cell, an electric cell. So whenever a current carrying coil is placed between two opposite poles of a magnet, this coil experiences a kind of rotational force which rotates the coil between these magnets if the coil is free to rotate. So this is the principle of electric motor. Watch here. When a current carrying rectangular coil is placed in an external magnetic field, a rotational force acts on the coil. This is the principle on which the electric motor is based upon. Now we will move to the construction of the electric motor. Watch here. This is the construction of an electric motor, and we will discuss the main parts of the electric motor. So an electric motor consists of the following main parts. What are these parts? Let's discuss. First one is permanent magnet. Watch here. The north pole of the magnet and the south pole of the magnet. Since the magnet does not move or the magnet remains stationary, that's why we are saying the magnet is permanent. The magnet does not move. So this is the pole P1 and this is the pole P2 of the permanent magnet. So we will say it consists of two poles P1 and P2 of a permanent magnet as shown in the figure. You can clearly see here the pole P1, which is north pole, and the pole P2, which is south pole of a permanent magnet. The next part is armature. Watch here. You can see here the coil A, B, C, D. This coil is called armature. Alright, this coil is called armature. So the rectangular coil ABCD is called armature, which is placed between the poles of the magnet. This armature coil ABCD is placed between the poles of the magnet. Now the next part is commutator. What is commutator? Watch here. These rings R1 and R2, these two rings are called commutator. These two rings act as the commutator. Alright. So the split rings R1 and R2 act as the commutator. The ends of the coil are connected to the split rings. Watch here. These two split rings means these are splitted. These are not connected to each other. These two split rings act as commutator. Commutator means which directs the current flow. The direction of the current flow must be in a single direction. The current flow must be in a single direction. So this device directs the flow of the electric current. And the ends of the rectangular coil means the end at C and at D. These two ends are connected to the commutator or the split rings. Now the next part is brushes. Watch here. This B1 and B2 are the brushes which are pushed against the split rings. These are called brushes. So a pair of carbon brushes, the brushes are made up of carbon. A pair of carbon brushes B1 and B2 is fixed to push against the commutator. So B1, watch here, B1 and B2, these are the brushes which are pushed against the commutator. Now let's move to the working of the electric motor. How does this electric motor work? Watch here. You can see here, this is the north pole and this is the south pole, due to which the magnetic field is produced from north to south. From north to south, this is the direction of magnetic field B. Alright, now watch here. We will talk about this side which is AD. In the side AD, the current is flowing like this. The current is flowing like this. So the direction of the current is this, and the direction of the magnetic field is this. Current is in this direction, the magnetic field is in this direction. With the help of Fleming's left hand rule, we will define the direction of the force, which will be downward. You can apply the left hand rule, Fleming's left hand rule here, and you can get the direction of the force, which is downward. So in the side AD, the direction of the force is downward. Now let's talk about the side BC. The side BC, the magnetic field is towards this direction, the electric current is towards this direction. So applying the Fleming's left hand rule, we will get the direction of the force, which will be upward. The direction of the force will be upward. So in the side BC, the direction of the force is upward. Due to these two forces, these two equal and opposite forces, the coil will rotate like this. So watch here. When the electric current is supplied to the circuit, then the electric motor starts to work in the following steps. What is our first step? Watch here. Step 1. According to Fleming's left hand rule, the side AD experiences a downward force. This is the side AD experiences a downward force, we have discussed, while side BC experiences an upward force. The side BC, this experiences a force, an upward force, we have discussed, due to which the armature rotates in anti-clockwise direction like this. Alright, now move to the second step. Watch here, step 2. So in this condition, you can see the side BC is in the topmost position, while the side AD is at the bottommost position, and these two split rings are adjusted like this. This is the intermediate position when the coil is rotating. So the coil is rotating in anti-clockwise direction in this position. Alright, moving to the next step. Here is step 3. So watch here, this is the north pole, the south pole. Now what happens? The side BC from here comes to here, and the side AD from here comes to here. Alright, you can see here we have completed half round. In the half round, the BC comes here and the AD comes here. Again, let's define the direction of the electric current. The electric current is supplied from here. The electric current is supplied from here means this is the direction of electric current. Alright, this is the direction of magnetic field. So the direction of the force will be downward. How can we decide? We can decide with the Fleming's left hand rule. The direction of the force will be downward. So in the side BC, there is acting a downward force. Alright, now let's talk about AD. In AD, the direction of electric current is this. So this is the direction of electric current, and this is the direction of magnetic field. So according to Fleming's left hand rule, the direction of force will be upward. So the side AC will experience an upward force, due to which this will rotate again in the anti-clockwise direction to complete its next half round. So watch here. According to Fleming's left hand rule, the side BC experiences a downward force. This is the side BC experiences a downward force, we have discussed, while side AD, this is the side AD, experiences an upward force. The side AD experiences and upward force we have discussed, due to which the armature rotates again in anti-clockwise direction, right? So due to which the armature rotates again in anti-clockwise direction. This again rotates in the anti-clockwise direction. So these three steps are responsible for the continuous working of the electric motor. Watch here. You can see here an electric motor which is continuously working. A continuous working motor is represented as given here. So after all, we have this, the continuously working electric motor. Now let's discuss the applications of electric motor or electrical motor. So what are the applications? Watch here. These motors are used in fans, blowers, pumps, turbines, ships, tools, used in machines, movers, rolling mills, compressors and paper mills. So these are the devices which are based upon the electrical motor, and there are some more devices. These are the most important devices in heating, ventilating and cooling, HVAC equipment. Alright, means refrigerator and air conditioning equipments, the motors are required. So these motors are highly used in the refrigerator and air conditioning equipments, and there are more motor vehicles and home appliances. Some more appliances are there, like washing machine, like mixer, juicer, which are based upon the electric motor. So these were the applications of the electric motor. That's all for now. See you again. Thank you.